Okay, for a theoretical calculus course, you're probably going to run into an instructor who's going to want to teach you the theory behind integration. So now that we've kind of got a handle on how to do integrate or how to integrate, now let's see if we can develop the concept of integration using theory. So summing it all up, before we get to the good stuff that we will use to evaluate definite integrals, we're going to go through what I call an initiation period. That'll give us some theory and tools to reach our goal. One of the first tools we're going to have to use is this sigma notation. So sigma notation is actually, if you want to sum n terms where the terms are a1, a2 out to an, then you can use this Greek letter sigma, I equal 1 to n, for a sub I. And what that means is I goes from 1 to n where I is integers. So 1, 2, 3, etc. So that would mean you do a1, a2, a3, an. And the lower limit here tells you where to start, and the upper limit here tells you where to stop. So here we're starting at 1 and we're stopping at n. And so some examples of that, a sub I can be thought of as like some function of I. That's one way to think of it. So here we're just going to sum the values for I from 1 to 5. So what is I when I is 1? Well, 1. What is I when I is 2? 2. What's I when I is 3? What's I when I is 4? What's I when I is 5? So that just means you sum the first 5 counting numbers 1 through 5. Now, if you want to sum, I meant to put an I squared here, so there's a square missing. So if it says sum I squared from 1 to 3, then you're going to sum, when I is 1, you're going to get 1 squared. When I is 2, you're going to get 2 squared. When I is 3, you're going to get 3 squared. And if you add those up, you'll get 14. Now here I want to sum I plus 1, but notice I don't have to start at 1. Notice I'm starting this at 3. So when I is 3, you get 3 plus 1. When I is 4, you get 4 plus 1. And I am stopping at 5 again, so you get 5 plus 1. And then if you add those up, you'll get 15. And so that's the sum sigma notation. Now, you can use this notation with variables, like if you said, what's the sum of ix from 1 to n? Well, that would just represent, when I is 1, you would get 1x. When I is 2, you would get 2x. When I is 3, you would get 3x. And then all the way out to I is n, you would get nx, and it would represent the sum of these terms. Now, you could use a different letter like k instead of I. Usually I, J, and K are the letters that are most commonly used for this index. So here, let's say we have 1 over n, so instead of a function of x, I got a function of n here, and then times k squared plus 1. So since n here is not affected by k, then you're going to have 1 over n, and then when k is 1, times 1 squared plus 1. And then when k is 2, you're going to have 1 over n times 2 squared plus 1. And then when k is 3, you're going to have 1 over n times 3 squared plus 1. And then when k is n, you're going to have 1 over n times n squared plus 1. And so forth. So there's two important sum properties that we need to talk about. One is the constant multiple property. So if you have the sum of k times a term, that's k times the sum of the terms. So in other words, if you have the sum of k times a term, then that's k times the sum of the terms. So if I have the sum from I equal 1 to 10 of 5i squared, well, that's the same as 5 times the sum of I squared from 1 to 10. Another example would be if you were going to sum two series or two sets of terms here, the sum of a sub I plus b sub I as I equals 1 to n, then that would be the sum of a sub I as I goes from 1 to n plus the sum of b sub I. So an example here would be if I wanted to sum I squared plus I as I goes from 1 to 19. Actually, I think I meant to put 10. So as I goes from 1 to 10, then that would be the sum of I squared as I goes from 1 to 10 plus the sum of I as I goes from 1 to 10. Looks like I zeros right next to 9, right? So then you can actually put these together. So if you wanted to sum 3i squared plus 5i minus 2 from 1 to 10, well, if you put these two rules together, you could rewrite that as 3 times the sum of I squared plus 5 times the sum of I minus the sum of 2 as I goes from 1 to 10. Now, there are some sum formulas that we could actually use here that are helpful. When you sum a constant from 1 to n, you're just going to get n times the constant. And like for instance, if you sum if you sum 5 from 1 to n, well, if you think about it, 5 is not affected by I, so basically you're adding 5 10 times. So if you add 5 10 times, you're going to get the same as 10 times 5, which is 50. Now, there's a story about Gauss creating this formula, but I'm not going to go into it here. But it's an interesting story if you want to look it up. But basically, this represents the sum of the first n whole numbers, or first n counting numbers. So for instance, if you wanted to add the first 6 numbers, first 6 counting numbers, then that formula is n times n plus 1 over 2, where n is the upper limit. So if I say, what's the sum of I from I equal 1 to 6? Well, n would be 6, n plus 1 would be 7, so I would just take 6 times 7 divided by 2 and get 21. Now, you can check this and see that if you add up those first 6 numbers, you're going to get 21. Now, obviously, if n went to a much larger number, then you would not want to have to check it, so we would rely on the formula. So if n was 100, if we were adding the first 100 counting numbers, then we would get 100 times 101 divided by 2, which is easy to solve with a calculator, 5050. Now, you probably don't want to check that one, but you could. Okay, and then I squared, we actually have a formula for I squared, and these formulas were proved with mathematical induction, by the way. So I squared is actually n times n plus 1 times 2n plus 1 all over 6. So if you wanted to sum the first 3 squares of the counting numbers, like 1 squared plus 2 squared plus 3 squared, you could use this formula where n is 3, so n would be 3, n plus 1 would be 4, and 2n plus 1 would be 7. And if you multiply that together, divide by 6, you get 14. And then you can easily check this and see that it works. The sum of those first 3 squares is 14. Now, but again, if you wanted to do the sum of the squares of, say, the first 10 numbers, you might prefer to go ahead and use this formula. So that would be 10 times 11 times 21, since n is 10, divided by 6, which is 385. You could probably check that one without too much difficulty if you wanted to, but certainly not if I wanted to go up to 100. Alright, and then we have one for the sum of I cubed. Well, the sum of I cubed from I equal 1 to n, so that would be like if we wanted the sum of I cubed from 1 to 3, that would be like summing 1 cubed plus 2 cubed plus 3 cubed. Well, there's a formula here. It basically says square n plus 1, and divide by 4. Well, multiply them and then divide by 4. So here n is 3, so 3 squared, and then we would add 1 to 3 and square that number, and then multiply the results, and then divide by 4. Well, if you multiply 9 times 16 and divide by 4, you're going to get 36. And again, you can check this by checking to see that 1 cubed plus 2 cubed plus 3 cubed does equal 36. Here I went only from 1 to 7, so if I go from 1 to 7, that's 1 cubed plus 2 cubed through the sum of 7 cubed. So using this formula, I would get 7 squared times 8 squared divided by 4, which is 784. And so you can use this to evaluate sums So now what if we throw in something like 1 over n in here? In other words, what if I say sum from 1 to 10 I plus 5 over n? Well, we could factor the 1 over n out because that doesn't depend on I. And then we could sum this, and then this can be broken up using the sum property, sum of I plus sum of 5. And we know we can sum I from 1 to 10 using the first rule, or the second rule I gave you up here. So that's going to be 10 times 11 over 2. And then, of course, the sum of 5 from 1 to 10, we can sum that using the first rule. And now that's going to be 55 plus, that's going to be 55 plus 50. So we're going to get 105 times 1 over n, which is 105 over n. Now, believe me, there's actually reasons for this. Now, but what if we wanted to do it not from 1 to 10, but from 1 to n? Okay, well that's a little bit trickier. I can still factor out the 1 over n. These should say n. Everywhere these should say n. Okay. Alright, so I can still do this, but now when I do the sum, I'm summing from 1 to n, so what I have to do is go up here and use this formula, n times n plus 1 over 2. And then the formula for sum of 5 from 1 to n would be n times 5, or 5n. Okay, so now what I did here, if you may not be able to tell here, but what I did is I factored out the n that I had here. And so when I factored the n out, I had n over n, so n over n is 1. And so basically that left me with n plus 1 over 2 plus 5. And then I just got a common denominator for 5. 5 is the same as 10 over 2. So this is going to be n plus 1 plus 10, which is actually n plus 11 over 2. So you can actually get an expression that represents this sum for any n value you wanted. So now let's see if it works for 10. What if I plug 10 in here? If I plug 10 in here, I get 10 plus 11. Let's see, 10 plus 11 is 21. That would be 21 over 2, which is what, 10 and a half. And then if I plug 10 in here for n, well, I would get 10 and a half. So yeah, it works for n equal 10. So it's probably going to work for any value of n. So make sure you learn these formulas and these properties because they're going to come in handy later, especially if your professor wants you to use these formulas to solve some integration problems. So I'm going to stop the video now, and I'll pick back up on another video for this section, and it's probably going to be at least 3 videos to finish this section.